In this lecture, we will talk about circular convolution. Our main objective is to implement the circular convolution as a linear transformation technique so that it can be performed using a computer. In the circular convolution, this equation is basically represents the analytical form where yn is the output, xn and hn, these two are two inputs. All the signals have same length, capital N, and in the second function is basically a specific kind of function which can be generated to circular time shifting process. Already we have seen in DFT time shifting video lecture. So now if we start thinking about this specific function, second function, it can be produced from h of k. It first passes through a circular reverse time operation that gives h of minus k. After that, if it is passes through a linear right shifting process, effectively this is anti-clockwise rotation, that would produce a final form h of n minus k modulo n. Now for a specific example, n equals to 4 is the analysis equation. Now we try to find out the second function individual signal elements so that it can be useful to write down this analytical form of yn. Let's say h of k, that is effectively equals to h of k mod 4, which is the original sequence h of 0 to h of 3. Now h of minus k, that associated to a specific value of n, which is n equals to 0, that is from this particular function which requires to compute y of 0. So h of minus k is basically the circular reverse shifting. So this can be directly found from the original sequences such a way that first sample point will be in the same place and rest of the sample points will be written in a reverse order. Now for n equals to 1, second function form is h of 1 minus k modulo operation 4. This is effectively a right shifting of the previous sequence h of minus k. If we take a right shift, so this is h1 will come first, then h of 0, h of 3, h of 2. Similarly for n equals to 2, h of 2 minus k modulo operation 4, this is h of 2, then h of 1, h of 0, h of 3. For n equals to 3, this is h of 3 minus k. This is just nothing but a right shifting of the previous sequence. Is h of 3, then h of 2, h of 1, h of 0. So we found all the individual element sequences for second function corresponding to each n value. Now we can write down the output sequence for y0 for n equals to 0, y1, y2 and y3. As you can see that this is nothing but a linear combination of the first function, and the linear combination coefficients are coming from the second function, and the coefficients for different output samples are having different arrangements or different orders. So if we just collect these orders, collect these samples weighting factors accordingly, then we can form a transformation matrix where left hand side is output vector, signal vector, and right hand side rightmost matrix is basically the one of the input signal vector, and the transformation matrix is basically formed by the another input vector. It's spatial arrangement. Now if you start thinking about computer programming approach, so this is our computer programming algorithm where it takes two input xn and hn. Input vector shape is n, 1, and this is also n, 1. So let's say this is working as a second function. So we are forming this particular matrix from the signal vector hn, and its shape is n, n. Now we are multiplying this matrix with the xn vector. We are multiplying these two matrices, that would produce me yn as we have seen earlier, and its shape is n, 1. So this is the way of implementing circular convolution in a computer programming. That's it. So now in next topic we will discuss about how circular convolution can be related to linear convolution, and how DFT can be used to compute LTI system output.